Welcome to Systemic Stack. My name is Kabir Anand. This is episode 9 of the System Engineering series, and today we will explore synchronous versus asynchronous systems in a way that helps you prepare for system engineering interviews on this topic. Deciding between blocking calls and eventual processing really dictates how your architecture handles scale and failures. We'll dive into these patterns so you can clearly justify why you choose one over the other when an interviewer probes your design for bottlenecks. This lesson opens with an exploration of core communication patterns, because how your components talk to each other fundamentally changes how your system scales and handles failure. We'll start by breaking down the mechanics of blocking calls and immediate responses, then compare those against non-blocking execution and background processing. It's really about understanding the performance impact when you're choosing between waiting for a thread or running tasks in parallel. From there, we'll dive into the reliability side of things, looking at how retries prevent cascading failures in synchronous setups versus how message queues provide durability when things go wrong in async flows. You'll see these concepts in action as we look at real-world examples like REST and Kafka, which often come up in interviews when you have to justify choosing a specific architecture for a data pipeline or a user-facing API. We'll wrap up by looking at the specific trade-offs between simplicity and scale. By the end, you'll have a clear decision framework for selecting the right pattern for your next microservice. When we talk about synchronous versus asynchronous systems, we're really discussing the flow of control and data between components. In a synchronous world, the caller sends a request and just sits there, waiting for the result before it can do anything else. It's like a phone call where both parties have to be present. The consequence of this choice is that it ensures that when the call returns, you know exactly what happened. But this simplicity has a dark side. If the receiver is slow or hangs, the caller is stuck, wasting precious memory and CPU time doing absolutely nothing. In a high-stakes interview, showing you understand this link between communication and resource management is crucial. A common failure mode here is the cascading failure, where one slow service backpashes everything else until your whole stack is unresponsive. On the other hand, asynchronous systems let you fire and forget, which is great for throughput but introduces complexity in tracking the state of a request. Getting this choice right is the hallmark of a senior engineer. Communication patterns are the foundation of how your components interact, and they dictate the ceiling of your system's performance. At the core, it's about whether you're coupling the timing of the request to the timing of the response. The impact on your behavior here is that it determines how you handle load spikes and partial outages. If every part of your system is tightly coupled synchronously, a single bottleneck in a deep microservice chain will throttle your entire user experience. You'll see this manifest as high latency and timeouts that are hard to trace. Interviewers love to see if you can identify these potential choke points early on. The failure mode to worry about here is tight temporal coupling, where your system cannot function unless every single piece is up and fast at the exact same time. By shifting to asynchronous patterns where it makes sense, you decouple these components, allowing the system to be more resilient and elastic. It's about trading off immediate certainty for better overall availability and efficiency across your entire infrastructure. Let's look at blocking calls, which are the backbone of synchronous communication. How this works is simple. When a thread makes a request, it essentially goes to sleep and waits for the server to send back a response. This is significant because it keeps the programming model very straightforward. You don't need to worry about state transitions or callbacks because the next line of code only runs once the data is ready. However, the failure mode is quite dangerous. Thread exhaustion. Each of those waiting threads consumes memory, and if you have a slow-running downstream service, your entire pool of threads can fill up with workers that are just sitting idle. In an interview, you should point out that while this is easy to debug, it's a huge bottleneck for high concurrency systems. If you don't implement proper timeouts, a single slow database query can lock up your entire application server. It's a classic trade-off where you trade scalability for simplicity, and knowing when that trade is no longer worth it is key. The immediate response model is all about providing a definitive answer within a single transaction loop. How it works is that the server processes the request and sends the final result back before releasing the connection. The practical impact of this is that it provides strong consistency. The client knows immediately if the operation succeeded or failed without having to poll or wait for a notification later. It's perfect for things like authentication or checking a bank balance where you can't afford to be eventually right. But the failure mode here is a lack of flexibility. If the server is under heavy load and can't provide that immediate answer, the request simply fails or times out, leading to a poor user experience. In system design discussions, you'll want to highlight that this pattern can't easily handle long-running tasks. If you try to force a heavy data processing job into an immediate response loop, you'll likely hit gateway timeouts and leave your system's resources tied up far longer than necessary. Non-blocking execution changes the game by allowing the caller to initiate an action and then immediately move on to other work. How it works is that the system uses mechanisms like callbacks, promises, or futures to handle the result whenever it eventually arrives. The reason this is such a powerful approach is that it maximizes resource utilization. Your threads aren't sitting idle waiting for I/O, so a small number of threads can handle thousands of concurrent connections. It's why frameworks like Node.js or Vertex are so popular for high-throughput APIs. However, the failure mode you have to watch for is callback hell or complex state management. When you don't have a single linear execution path, it becomes much harder to reason about the order of operations or handle errors gracefully. In an interview, it's vital to mention that while non-blocking systems scale beautifully, they require much more sophisticated observability and error handling logic to prevent silent failures where a request is lost in the shuffle and never actually completes its lifecycle. Eventual processing takes the non-blocking idea further by decoupling the request from the execution entirely, usually through a message queue. How it works is that a client drops a message into a buffer and a separate worker process picks it up whenever it has capacity. This approach is vital because it provides incredible durability and load leveling. If you get a sudden burst of traffic, the queue acts as a shock absorber, so your workers don't get overwhelmed. The failure mode here, though, is the loss of real-time feedback. Since the user doesn't get an immediate result, you have to design the UI to handle an in-progress state, which adds complexity. Interviewers will look for your ability to explain how you'd handle poison pill messages, tasks that keep failing and could clog up your queue indefinitely. You need to account for dead letter queues and retry policies to ensure that a single bad task doesn't stop the entire processing pipeline from moving forward for other users. When we compare latency, the difference between waiting and parallel execution becomes stark. In a synchronous chain, if you need to call 3 services that take 100 milliseconds each, your total time is 300 milliseconds. How this works is cumulative. Each step is a sequential bottleneck. The real effect of this sequential approach is that as your microservice graph grows, your tail latency, that 99th percentile, explodes, making the app feel sluggish for many users. The failure mode is latency amplification, where a tiny bit of slowness in a low-level service ripples upward, causing timeouts at the edge. Conversely, with an asynchronous or parallel approach, you could trigger all 3 calls at once and be done in just over 100 milliseconds. In a design interview, showing the math on these latency savings is a huge plus. You're essentially trading a bit of architectural complexity to buy back hundreds of milliseconds for your users. Just remember that parallelizing everything isn't free. You'll need more concurrent connections and a way to aggregate those results back together once they arrive. Scalability and throughput are where asynchronous systems really shine. How it works is that by avoiding blocking, you ensure that every CPU cycle is spent doing actual work rather than waiting on a database or a network call. This efficiency is what allows you to handle far more requests per second on the same hardware compared to a synchronous setup. One simple way to picture this is a restaurant where the waiter doesn't stand at the table while the chef cooks the meal. They're free to serve other tables in the meantime. The failure mode here, though, is resource exhaustion elsewhere in the system. Because the entry point can accept so many requests, it can easily overwhelm downstream databases or legacy services that aren't built for that kind of volume. In an interview, you've got to discuss back pressure. If your async pipeline is pushing data faster than your database can write it, you'll eventually run out of memory or crash. Balancing this flow is the difference between a high-performance system and a chaotic one. Resilience in synchronous systems usually comes down to how you handle immediate failure. How it works is that if a service call fails, the client must decide right then and there whether to try again or give up. Having a solid retry strategy is essential because a well-implemented retry policy can mask transient network glitches and keep the system feeling stable. But the failure mode is the retry storm. If a service is already struggling and all its clients start hammering it with retries at the same time, you'll effectively launch a self-inflicted DDoS attack that prevents the service from ever recovering. In an interview setting, you should always mention exponential backoff and jitter as your defense mechanisms. These ensure that retries are spread out over time, giving the failing service some breathing room to reboot or clear its backlog. Without these, your synchronous resilience strategy might actually become the very thing that takes your entire platform down during a minor blip, leading to a much larger and more painful outage. In asynchronous systems, we achieve durability by using persistent message queues. How it works is that once a message is accepted by the broker, it's written to disk. Even if the consumer service crashes or the power goes out, that message stays safe until it's successfully processed. The core value of using a broker is that it guarantees no work is lost, which is vital for things like order processing or billing. The failure mode, however, is queue buildup. If your consumers are slower than your producers for an extended period, your queue can grow until it runs out of disk space or causes massive lag. In an interview, this is where you talk about monitoring consumer lag and scaling your worker pool dynamically. You also have to consider what happens if a message is processed twice and at least once delivery guarantee. Designing your consumers to be idempotent so they can handle the same message multiple times without side effects is a critical step in making an asynchronous system truly robust. Choosing between APIs and event-driven patterns depends entirely on the user's needs. Synchronous REST or GraphQL APIs are usually the way to go for user-facing interactions. How it works is that the user gets a response right away. And the reason we prioritize this for the front end is it matters for things like logging in or searching for a product where they're actively waiting for the screen to update. The failure mode here is a poor user experience if the backend is slow. The user sees a spinning wheel and might just leave. On the flip side, asynchronous event-driven patterns are perfect for background jobs like sending emails or generating reports. The user doesn't need to stay on the page for that. But the failure mode there is lost context. If something goes wrong in the background, the user might never know why their email didn't arrive. In an interview, emphasize that you choose the pattern based on the latency budget and the consistency requirements of the specific feature you're building. The trade-offs between these two patterns often boil down to complexity versus capability. Synchronous systems are much easier to build, test, and debug because the flow of logic is linear. How it works is predictable, and this is a major consideration because it matters when you're moving fast and need to ensure high data consistency. The failure mode, as we've seen, is that they don't scale well and are prone to cascading failures. Asynchronous systems offer incredible scale and robustness, but they introduce a lot of moving parts, like brokers, dead letter queues, and complex state machines. This increases the cognitive load on your team and makes the system harder to observe. In an interview, a great answer acknowledges that there's no free lunch. You might start with a synchronous approach for an MVP to save time, but you should have a plan to migrate critical paths to asynchronous patterns as your traffic grows. Being able to justify exactly when to make that jump shows you've got real-world architectural experience. Let's put this into practice by looking at REST versus Kafka. REST is the king of synchronous communication. How it works is over HTTP, where a client waits for a specific status code. Its widespread adoption is due to it being a universal standard that every developer understands, making integration simple. But the failure mode is that it's inherently point-to-point. If the endpoint is down, the request is dead. Now look at Kafka, which is the gold standard for asynchronous event streaming. How it works is by decoupling producers from consumers through a distributed log. This allows multiple different services to consume the same data at their own pace, which is perfect for microservices. The failure mode here is operational complexity. Running a Kafka cluster isn't trivial, and you can run into issues like partition imbalances or disk pressure if not tuned correctly. In an interview, comparing these two shows you understand that your choice of tool should match the communication pattern the business problem actually requires. When you're deciding on a pattern, a simple decision tree can help guide you. First, ask yourself if the user is waiting for an immediate result to take their next step. If yes, go synchronous. How it works is you provide that instant feedback, and this helps you maintain a smooth user journey. But watch out for the failure mode of long-tail latency, making the app feel broken. If the task can happen in the background, go asynchronous. How it works is you use a queue to decouple the work, which provides much-needed system stability and throughput. The failure mode here is that you now need to handle eventual consistency, where a user might not see their change reflected immediately. In a system design interview, this is your chance to show you're thinking about the human side of the system. It is not only about the bits and bytes, it's about matching the technical architecture to the user's expectations, while ensuring the system doesn't buckle under heavy load. We've really zeroed in on the core of how systems communicate. On one hand, you've got synchronous calls, where the client just sits there waiting, which is great for instant consistency, but tough on scalability when those service chains get long. On the other hand, we looked at how asynchronous systems use non-blocking patterns to keep the engine running, prioritizing throughput over immediate feedback. In a high-level design interview, this is where you show your depth. You aren't just picking a tool, you're deciding between resource efficiency and execution simplicity. Understanding that trade-off, knowing exactly when to use a direct REST call versus a message queue like Kafka, is what separates a senior engineer from the pack. You've now got the framework to balance latency against system availability without breaking a sweat, and that's a huge win for your architectural toolkit. So, that wraps up our look at sync versus async communication. In a high-stakes interview, don't just pick a pattern. You've got to explain the why. Justify your choice by weighing the simplicity of a REST call against the massive durability of an event-driven queue. Show the interviewer you're thinking about failure modes, like how a synchronous bottleneck can cascade and take down an entire service chain. If you found this helpful, definitely subscribe to the channel for more technical breakdowns. I've put all the course details in the description for you to explore further. Keep practicing those architectural trade-offs, and I'll see you in the next session. Good luck with your designs.